Hi, and welcome to the Midrange Electronics Enhanced Midrange PIC C tutorials. In this first lesson, we'll take a look at one of the smallest of the modern PICs, and start by simply lighting an LED. These videos are intended to be a companion to the Enhanced Midrange PIC tutorials, the introductory lessons of which are available as free downloads from the Midrange Electronics website. They go into more detail than is possible in the video lessons, so it's best to download the tutorials, pause the videos whenever you want, and refer to the written lessons to fill any gaps. To program PICs, you'll need a development environment, what's called a toolchain. Setting up the development tools was covered in the introductory videos, but briefly in these tutorials we'll be using the MPLAB X IDE, and I'll run it under Windows, although you should be able to follow along just fine if you're using Linux or a Mac. The PICkit 3, PICkit 4 or Snap Programmer, and the Midrange Baseline and Midrange PIC Training Board. And to program in C, you'll also need a C compiler. We'll be using Microchip's XC8 compiler, which is a commercial product, but we'll be running it in free mode. In free mode, some optimizations are disabled, so it generates bigger, slower code, but for most purposes it's perfectly fine, as we'll see. To download the latest version of XC8, go to microchip.com. Microchip seem to rearrange their website fairly often, but when I made this video, the XC compilers are under Design, Development Tools, Software Tools for PIC MCUs, XC compilers. Then find the XC8 compiler for your system under the Downloads tab and download it. When you run it, sign your life away to Microchip, then select the free license type. Now it's Next, Next, Next. And after the install is finished, you're given a chance to try a free trial of the Pro license, but there's really no need, so you can just hit Next again, then Finish. XC8 is installed. Before we use it though, we'll start by taking a look at one of the simplest PICs that's still reasonably current, the 12F1501. So what do I mean by reasonably current? PICs have been around for a long time. They actually date back to the 70s. At first, Microchip just released new variations on the original design, while the core architecture, the instruction set, the way the chip's organised, remained the same. These days, that original design is called the Baseline PIC architecture. Microchip later developed a higher end architecture, used in the PIC 18 family, and in between was the mid-range architecture, used in PIC 12 and PIC 16 devices. But the mid-range still had some significant limitations, so Microchip eventually developed the enhanced mid-range architecture to replace it. It's better for C compilers, it makes output operations easier, and it has some more advanced peripherals available for it. So unless you really need a tiny 6-pin package, or to save money, the enhanced mid-range devices are the lowest end PICs that you should be using these days. I can't go into all the details in a video. As I said before, you should refer to the written lessons for that. But the ultimate reference for any PIC is a starter sheet, which you can download from microchip.com. Now sometimes the data sheets contain errors, but even if you're working from tutorials, you should consult the datasheet as well. The 12F1501 comes in various 8-pin packages. The DIP version is easiest to prototype with. 2 of the pins are for power, which can be up to 5.5 volts, and ground. The remaining 6 pins are for input and output. They're the PIC's connection to whatever devices it's responding to or controlling. They're named RA0 to RA5. There's a lot of functionality available through those pins. Analog inputs, comparators, timers, oscillators, PWM outputs. We're going to start with basic digital input and output, then move on from there. A nice thing about programming in C is you don't need to know all the gory details of the PIC's internal architecture. The C compiler hides a lot of it from you, so don't let this diagram scare you. Okay, this one's a little simpler. You do need to be aware of some internal details. Enhanced mid-range PICs, such as the 12F1501, contain flash memory, which holds the program code that the PIC's running. The PIC also has some RAM, where the C compiler will place your program's variables and data. But note that the contents of RAM are lost when the PIC loses power. The I/O pins, and peripheral functions like timers and so forth, are accessed through registers that the CPU can read from and write to, just like accessing RAM. The I/O pins can be set up as either inputs or outputs, hence the name I/O pins. Well, most of them anyway. RA3 can only be an input. Or, instead of being a digital input pin, it can be configured as the reset pin, also known as MCLR. Pull it low, and the PIC resets itself. Almost the same as if you turn the power off then on again. Taken together, the 6 I/O pins are referred to as port A. Bigger PICs have extra ports, port B, port C and so on. They all work pretty much the same way as port A. The port A register gives you direct access to the current value of the I/O pins. We'll take a look at this in a later lesson on reading switches. But briefly, if a pin is being held high, the corresponding bit in port A will read as 1, otherwise it reads as 0. Now that's true regardless of whether the pin is configured as an input or output. It doesn't matter whether the PIC is driving the pin, or if an external device is driving it, or even both. The port A register tells you what the actual state of each pin is. The TRIS A register controls the pin directions, whether each pin is an input or output. By default, the pins are all configured as inputs. That's to avoid damaging anything connected to them before you've had a chance to set things up. To configure a pin as an output, clear the corresponding bit in the TRIS A register. When a pin has been configured as an output, that pin will be driven high if the corresponding bit in lat A is set to 1. So for example, if RA1 has been configured as an output pin, setting bit 1 of lat A to 1 will drive RA1 high. So to light an LED, we need to connect it to one of the I/O pins, clear the corresponding TRIS A bit to configure that pin as an output, and set the corresponding bit in the lat A register to drive the pin high. Here's a circuit for this example. It's pretty simple, eh? Just power the PIC from a 5V supply, add a decoupling capacitor on the power supply, and drive the LED directly from one of the output pins via a current limiting resistor. To build this circuit with the training board, insert the 12F1501 supplied with the board into the 12F socket, taking care to plug it in with a notch toward the top of the board. Enclose the jumper next to the LED labelled RA1. Every other jumper should be left open. If you have a PICkit 3 or PICkit 4 programmer, plug it into the training board with the arrows aligned, and connect it to a USB port on your computer. The PICkit can supply power to the board, so that's all the hardware you need for this lesson. If you have a Snap programmer, you'll also need to supply 5V to the training board's DC jack. Now we're ready to write our first PIC program. When you first run MPLAB X, you'll see the start page. You can access a lot of useful information here, but since we're starting a new project, we'll click on Create New under Projects. This will run the New Project wizard, which, as you'd expect, helps you to set up your new project. We're making a simple piece of code that will stand on its own, so I choose Standalone Project. Next, we specify which device we'll be programming. We're using a Midrange PIC, so select the Midrange family, and then the device, which in this case is a 12F1501. Some PICs can be debugged through a piece of hardware called a debug header, but we're not doing debugging in this lesson, so we can ignore this option. Now we need to tell MPLAB what programmer we're using. If yours is plugged in, it should show up in this list, identified by its serial number. As you can see, I've got a PICkit 3, a PICkit 4, and a Snap plugged in. I want to use the PICkit 3 for now, so I'll select that. We also need to tell MPLAB which compiler to use. You should see the XE8 compiler, which we installed earlier, listed here, along with the MPASM assembler, which comes with MPLAB X. We'll be using XE8, so I'll select that. The final step is to name your project and specify where it will be stored. I'll give it a snappy name, and then go find the directory I created when I downloaded the tutorials. By default, MPLAB X creates a separate .x folder for its project files, unless you select otherwise. I think it's needed to keep the MPLAB files separate, so I'll keep the default. And, since we have only one project, I'll select it as the main and only project. After you click Finish, your project will appear in the Projects tab. It's where you can access all the files, such as source code, that belong to your project. Source files contain the code that's compiled by the compiler. So we need to create at least one source file for each C program. You could just type them in from scratch. Luckily Microchip provides templates that you can use as a starting point. A convenient way to create a new C source file is to right click on source files, then choose New and main.c. Type in a suitable file name, leaving out the .c because the extension is added automatically for you. You can place the new source file into a specific folder if you want, but I'll just leave it blank so the file will be created in the projects folder, which is where you'd usually want it. the new file is automatically opened for editing in an editor window. But before editing a file, I want to set up the editor to work the way I like. So I'll go to Tools, Options, Editor, then the Formatting tab. Check the language is set to C and select your preferred formatting style, and customise it if you want. Personally, I like ANSI style, with the tab size set to 4 and spaces instead of tabs, but your mileage may vary. Okay, we can finally start writing some code. The first section of the template code is a block of comments, which I'll expand a bit, dividing it into sections. How you comment your program is up to you. Date and version number might be a bit redundant if you're using a version control system such as Git, but I fill them in anyway. I also document what processor family and device the program is written for, even though it's not hard to run the code on another PIC, because the C compiler takes care of a lot of the low-level details. Speaking of compilers, it's also a good idea to specify which compiler the program is written for, because code intended for one compiler won't necessarily compile on another. Of course, the most important part is to document what the program does. I usually include a short description, then some more detail. In this first example, we'll only turn on the LED. We'll blink it in the next lesson. It's also important that you document which PIC pins are used for what. We'll try to write code that makes it easier to change the pin assignments later, but they still have to be documented. XC8 programs should always start by including the xc.h header, which defines the symbols which make it possible to refer to the PIC registers, such as late A, by name. The template now jumps straight to the main program code, but there's an important part missing. The PIC has to be configured by setting up the configuration bits, which are sometimes called fuses. They specify how the processor should be configured before any code starts running. Now you could look up the datasheets and type in what are known as configuration parameters yourself, but there's an easier way. Get MPLAB to generate the configuration code for you. From the window menu, select Target Memory Views, Configuration Bits. Here you'll see all the configuration options applicable to your processor. If you ever move your code to another PIC, you should repeat this step, because different PICs have different configuration options. The PIC needs a clock or oscillator to operate. We'll look at clock options in a later lesson, but for a simple setup like this, the internal oscillator is fine, so I'll select that. The watchdog timer can be used to automatically restart your program if it crashes. We'll look at that feature in a later lesson, but we don't need it here, so I'll disable the watchdog timer for now. Master Clear Enable means that the RA3 pin will be configured as an external reset, and can't be used as an input pin. That's necessary if you're using the Snap programmer, and in any case, we don't need any input pins in this example, so I'll leave the MCLR pin enabled. Code protection is intended to make it difficult for anyone to read your code out of the PIC. We're not doing anything secret here, so I'm going to leave code protection off. The other options aren't important for now, but you should check that the low voltage programming option is set correctly. This affects how the programmer tells the PIC to enter programming mode. High voltage programming is the traditional method, and it's the most reliable, but the Snap doesn't support it, so we'll stick with low voltage programming, so this code can be used with any programmer. Once you've selected the configuration you want, click the Generate Source Code to Output button. MPLAB will generate appropriate pragma statements, complete with descriptive comments, which you can copy and paste into your code. It's pretty easy, eh? I'll just add a couple more comments. You're now ready to take a look at the main program. As usual for C, the main part of your program sits in a function called main. When the PIC starts up, it executes the compiler's initialization code, then it runs the main function. But unlike bigger computers, there's no operating system. Nothing calls main. If your program finishes, there's nowhere for it to go, nothing to pass control back to. So this return is a bit misleading. There's nothing to return to, so I'll get rid of it. Now let's add some code to turn on the LED. Remember that the LED is connected between RA1 and ground, so we need to drive RA1 high to turn the LED on. First, we need to configure RA1 as an output pin. That means clearing bit 1, because it's RA1, of the TRIS A register. XC8 makes it possible to access the PIC's special function registers, including TRIS A and that A, through variables defined in header files, which are included automatically when you include xc.h in your code. If you want to check how the various register variables are named, you'll find the header files in the PIC include folder under the XC8 installation. The symbols for the 12F1501 are defined in PIC 12F1501.h. There's a lot in there, isn't there? But here's the definition of tris-A, for example. Back to coding again, and the first thing to do is to clear bit 1 of tris-A to configure RA1 as an output. So I'll add some comments to say that we're initializing the PIC and configuring the port pins. We only care about RA1 because the other pins aren't connected to anything. So I could just clear tris-A to all zeros to configure all the pins as outputs, except of course for RA3, which always has to be an input. But I might as well leave the other pins in their default input state. So I could set tris-A to a binary value like this, where only bit 1 is clear. Or suppose this is part of a bigger program, where the other pins have already been set up, and you only want to affect pin 1, leaving the other tris-A pins alone. We could then use a binary operation like this, which uses the AND and left shift operators to only clear bit 1. You'll often encounter expressions like this, but modifying individual bits is so common that XC8 provides a mechanism for doing just that, through bit fields defined in the header files, which you can see for tris-A here. So we could instead write it like this. Since tris-A bits is a structure, MPLAB lets you select its elements from a list as you type, which means you don't have to remember as much, and it's harder to make mistakes. Now that we've configured RA1 as an output, we can make it go high, turning on the LED by writing a 1 to bit 1 of the lat A register. And, just like tris-A, we can access individual bits in lat A through the lat A bits bit field structure. Finally, remember how I said there's no operating system for the main function to return to? In a bare metal system like this, microcontroller programs usually never finish. Sure, they might shut the hardware down when they're done, but even then they usually just go into a dormant state and wake up to bring the system back to life. The program never actually finishes as such. So we need some code that will just keep running forever. It's usually called the main loop, and this structure, with initialization code followed by the main loop, is pretty common. Arduino people will recognise it, for example. Our main loop won't do anything, just has to sit doing nothing forever. So we could use an empty for loop like this. Or while one, if you prefer. Either way, that's the finished program. Now that we've finished our program, we need to compile it, and then load the compiled code into the PIC. But before the PIC can be programmed, it has to be powered. As we've seen, if you have a snap programmer, you'll need to supply power through the DC jack on the training board. But if you have a PICkit 3 or PICkit 4, you can configure it to supply the power. So let's go do that. Your project status is shown in the dashboard window. It shows what device you're programming, which compiler you're using, the tool you're using to program or debug the PIC, and how much of the PIC's memory is being used by your program. To configure your programmer, click on the project properties icon, which opens a window where you can change or configure the tools you're using. Since I'm using a PICkit 3 at the moment, PICkit 3 appears in the category tree, so I'll select it. There are a few option categories, but the one we want first is the power option. You'll need to select power target circuit from PICkit 3, and a voltage of 4 to 5 volts is fine for PIC 12F1501, but note that if you're using the LF version of the 1501, it's important to limit the supply voltage to 3.3 volts or less. You should also check program options. Remember how we selected low voltage programming mode as part of the processor configuration? The programmer has to be configured in a matching way, so it's important that low voltage programming mode also be enabled here. There's also a programming speed option, which can make the programming process faster, at the cost of being potentially less reliable. Slowest is fine for a tiny little program like ours, and the recommended programming method will be fine too. The other option categories, such as memories to program or freeze peripherals or firmware, aren't important for now, so you can just leave them all at their defaults. If you have a PICkit 4, you'll see many of the same options, but just to be confusing, some of them have different names. You'll still need to enable low voltage programming mode under program options. Program speed doesn't give you as many choices as the PICkit 3, but that's okay. Normal speed will do fine. In the power category, I'll select power target circuit from PICkit 4, and although I could leave the voltage level at 5 volts, I might as well change it to 4 volts to be the same as my PICkit 3 setup. The remaining options can all keep their default values. If you have a snap programmer, you don't get as many options. There's no power category because the snap can't provide any power. And there's no choice of programming mode. It only supports low voltage mode. In fact, with a snap programmer, you can leave every option set to its default value. Compiling your program is called building the project, and you can do that through menus or keyboard shortcuts, or you can just click one of the toolbar icons. The hammer icon builds your project. This process leaves intermediate files behind, which can save some time when the project is next built. The hammer with the brush cleans out those files first, and then builds everything again from scratch. There's usually no need to do that though. The run icon builds your project, programs it into the PIC, then starts running. The icon with the downward arrow loads your program into the PIC. It automatically builds your project first, so usually you just make some changes to your code, then click this icon, and MPLAB will build the project, and if your program compiles without errors, it'll load it into the PIC, all in one operation, which is effectively the same as what the run button does. Either way, it's one click to build, program and run. So let's click it and see what happens. You can see the compiler output in the output window. The code compiled without errors. So now MPLAB connects to your programmer, supplies power, and programs the code into the PIC. The code starts running and the LED lights. Okay, that was a long lesson, and we've only lit an LED, not even flashed it. Gets easier from here though, because all the tools are set up, and now you know how to use them. In the next lesson, we'll make that LED blink. See you then.